She teaches Newton's law of cooling in that class, so students who've had her normally are a little bit used to that already. I don't teach it in Cal 2. All right, this is lecture 5. We're about the halfway point now. We're going to do some applications. The first application we're going to talk about is an orthogonal trajectory. Sounds like something very complex and complicated. It's going to be easy to do this. If I gave you a graph of a family of curves, you know when I say a family of curves, that means there's a C in there that constants can be put in, and the graphs are just going to either be moved somehow. Looked all the same shape, but if you were to graph them all in the same coordinate plane, if I did f of x equals x plus, or x squared plus 1, f of x equals x squared plus 2, f of x equals x squared plus 3. Y'all know those are all the U shape. They just moved in different positions on the coordinate plane. If I graphed a family of curves in the coordinate plane, let's say I need to find another family of curves that will intersect those graphs all at perpendicular lines. They need to cross each other at 90-degree angles. That's the word what orthogonal means. You probably remember that from Cal 3. When vectors were orthogonal, it means they crossed at perpendicular lines, 90-degree angles. That's another word we use, orthogonal. When all the curves of one family intersect orthogonally or at right angles, all the curves of another family, then the families are said to be orthogonal trajectories of each other. In other words, an orthogonal trajectory is any curve that intersects every curve of another family at a right angle. Orthogonal trajectories occur naturally in the construction of meteorological maps and in the study of electricity and magnetism. I've seen books, physics books and that kind of science books where you saw the magnetic poles on the Earth even, and you see the graph of how those magnetic fields work. This is something that you might see orthogonal trajectories come up in. For example, in an electric field around two bodies of opposite charge, the lines of force are perpendicular to the equipotential curves, that is, curves along which the potential is constant. That's just an example where you might see this. Now, in early algebra class, orthogonal, I said, was another word we used for perpendicular. What did you learn about the slope of perpendicular lines? Y'all remember that? 1 over, so you flip it, right? What else do you do? Make it negative. You change the sign. For example, if I said a line has got a slope of 2, what would the slope be of a perpendicular? Negative 1/2. You flip it and change the sign. Okay? You guys know that a derivative is the slope of a tangent line. It's the first thing we learned in Cal 1. So we're going to use that concept to do orthogonal trajectories. There's a picture of two, you can't hardly see. One's broken graphs and the other are solid graphs. But those families of curves graphed there are orthogonal trajectories of each other. The original picture was black and white, and so that one looks a little distorted too. But the broken lines are orthogonal trajectories to the graphs that are solid lines. Looks like some kind of bug, doesn't it? Or space alien creature. Method. To find the orthogonal trajectories of a given family of curves, we first find the differential equation that describes the family. Just like you did here. We wanted the differential equation that describes this family of curves. So you're going to go back and do that again. That's why we had to learn that earlier. Okay? You're going to find the DE that matches this family of curves. Once you do that, the differential equation of the second an orthogonal family, you're going to flip what you get up there and change the sign. Flip it and change the sign. Remember from elementary algebra that perpendicular lines have slopes that are negative reciprocals of each other. So you're going to form a new differential equation by flipping it and changing the sign, and then you solve that DE. And that'll find your new family of curves that are orthogonal trajectories from your original. Let's do an easy problem here. I want the orthogonal trajectories for the family of curves given by these hyperbolas. Does anybody remember what the line y equals 1 over x looks like when you graph it? Remember that from pre-cal days? You remember what those curves look like? 1 over x? Yes, absolutely. Good job. Hyperbolas in quadrant 1 and 3. So family of those would be any number replacing the c here. So if I had a negative number in there, it could be curves that happen over here, here also. So it could be any number of different curves. What I'm wanting is to come up with a new family of curves that I could graph that would cross those at perpendicular lines. At perpendicular lines. So let's see what we can do with that. Use up all my space with that. Okay. So I need to find first of all, I got to find a differential equation for that family of curves. So we're going to take, there's only one constant, so I need to take one derivative is all I should ever have to do. Y prime would equal what? We could think of this as what? C1x to the minus 1? Can we think of it like that? Could you think of it that way? So the derivative would be what? Negative c x to the minus 2. He is exactly right. Which would actually be, we want to write that differently, negative c1 over x squared. Could you do it like that? Also, in that original statement there, what is c1 equal to? Multiply together, right? You could just cross multiply there, y times x. So let's see what we got here. Y prime equals negative xy over x squared. How's that going to clean up? Okay. Okay, so there's a differential equation for that first family of curves. That explains that one. Now we want to find the orthogonal trajectory. So what we're going to say then is we're going to reverse this process. Take this up here. This becomes dy over dx equal to what? If I want something orthogonal, we're going to flip it and change the sign. So what would I have? Positive x over y, right? So when I flip it and change the sign, my differential equation is going to be positive x over positive y. Now just separate your variables, do separation of variables, and integrate. So it'll be y dy equal to x dx. That's your dream equation, isn't it? It's a dream come true separation of variables problem right there. Integrate both sides. What is the integral of y? So y squared over 2, good job, equal to x squared over 2 plus c. Okay, what could I do to make it look better? Clear the 2, so y squared equals x squared plus c. Now, one thing this is fine. You can leave this alone like you want to, but if you want to kind of make sense of it a little bit better, those of you who remember any of this stuff, you may have to be refreshed. But if I subtracted that x squared back over with the y squared, do you remember what that gives me? Not a circle. You're in the right kind of idea, but what? Not circle. Not the ellipse either. If it's an ellipse or a circle, it's going to be plus. Hyperbola. So it's a different kind of hyperbola there. Now, if I were to get the graphing calculator in here and graph several graphs, put different numbers in for C, graph several of those in the intersection. They're orthogonal, or they have orthogonal trajectories. So there's a couple of steps to it. You got to find the differential equation first, flip it, change the sign, and then solve it. Okay? To find the orthogonal trajectories for it. Let's do one more. I think I may have a picture of this one. Yeah. In the book, I think that I copied that picture from. One was a different shade than the other. Of course, that looks just black and white. Can you see what I'm talking about? How the different curves when they cross at 90-degree angle. You can have a T there. Okay. So let's do one more of those. There's only one c, so you should only have to take one derivative. And question, how am I going to take the derivative of that problem? A blast from the past. Quotient rule. Before I even tear into that quotient rule stuff, let's go ahead and solve that thing for C1. Let's go ahead and see what my substitution for C1 will be. C1 would equal y times x, 1 plus x, divided by x. Y'all check my algebra. Y'all agree with that? C1 would be you cross multiply y times the 1 plus x and then divide by the x. So that's what I'm going to use for my substitution in a minute. So y prime, y'all told me that would be quotient rule. So f prime g, the top would be f prime. So C1 times g, 1 plus x, minus f times g prime. What's the derivative of the denominator? 1 over g squared. So that's 1 plus x quantity squared. And I think we can clean that up even better before we try to put our C stuff in there. That's going to be C1 plus C1x minus C1x. Look at that. Y'all see what happens up top? Let's subtract off. Okay, so let's back substitute here. So y prime equals C1, which was y right here. Right here. Oh, my stupidity. I see what you're talking about. Thank you. I'm glad you picked that out. I didn't even know why I did that. Let's see here. Good. I wasn't figuring where you was talking about, but now I see it clearly. Okay, so C1 was y times 1 plus x. That's on top. Over x, so I'm going to put an x in the bottom. And you already got a 1 plus x squared down there. How's that going to clean up? One of those is going to cancel out, right? I agree. dy over dx equals y over I can go ahead and multiply all that, couldn't I? X plus x squared. So x plus x squared. Whoops, I'm sorry. What did I do wrong? Too many steps. I'm getting too old to remember all this. What? Flip it, okay? Let's put a note to ourselves. Flip and change the sign. So dy over dx equals, I'm going to do it this way. I'm going to put x plus x squared on top. And since it's, I'm going to do negative y. As long as I put a negative in there somewhere, it's okay. Got to flip and change the sign. So when I separate that, I get negative y dy equal to x plus x squared dx. Integrate both sides. So that's negative y squared over 2 equal to, okay, what's the antiderivative of x? X squared over 2 plus antiderivative of x squared. Algebraically, what else could we possibly do here? How about, he said multiply through by negative 2. What's better? Multiply through by negative 6. Negative 6 would give me 3y squared equal to 3x squared, or negative 3x squared plus minus 2x cubed plus c. You know what? If you'd have left it alone, I'd have been happy even with this. There's really not much you can do to make it pretty. So once you find yourself a differential equation, flip it and change the sign, and then you should be able to use separation of variables. So on the quiz next week, you'll have one question like this. One problem. I think on the homework set, there's a couple of practice problems. Okay? Look at these two examples. Look at practice. And by the way, not that I'm trying to be a smarty pants or anything like that. I'm just being honest with you guys. Quiz 2 that you got back tonight, every single problem on the quiz, was an exact problem from the problem sets. Every problem came straight off the problem sets. So you supposedly had already worked all of those before. Okay, so if you're not spending the time doing any of the practice homework, that might be incentive to start, right? I mean, I kind of felt bad if it's too hard, but then again, I'm like, I gave them all these problems already before in the past, so y'all already had every one of them. I got straight off the problem set. I didn't look them up and find a new problem. It was straight off the page. So make sure y'all are doing the practice work. Exponential growth and decay. Y'all already know a lot about this probably. How many of you ever had problems where you had to find compound interest in banking? Okay, we do that in pre-cal here. That's one of these applications. Or working chemistry. Have you done anything with radioactive elements, half-lives, that kind of thing? That's this kind of issue. An initial value problem. Dx over dt equals kx, where x of t sub 0 is equal to x of 0. K is a constant of proportionality. You're going to spend a lot of your time trying to figure out what this k is. Solving for that k first, the constant of proportionality. And this occurs in many physical theories involving either growth or decay. For example, in biology, it is observed that the rate at which certain bacteria grow is proportional to the number of bacteria present at any time. Over short intervals of time, the population of small animals, such as rodents, can be predicted fairly accurately by the solution of differential equations. Any of y'all deer hunters? Okay, y'all need to look up the logistic equation and find out about, there's problems all over the place about deer populations. Okay, how you can predict, one year there was this many, supposedly this many deer in this area, and then 5 years down the road, what's your prediction on? I mean, there's stuff like that you can find if you're interested in that kind of thing. In physics, an initial value problem provides a model for approximating the remaining amount of substance that is disintegrating or decaying through radioactivity. For example, if I had a big block of plutonium and I just set it out here on top of this desk, we would all die of cancer really quick. But it's going to, over time, decay, evaporate, disintegrate into the atmosphere. Okay? Radioactive elements do that. That's why they use those kind of they have the what's the word I'm looking for? They don't behave well. Radioactive elements don't behave well. That's why they're great for stuff like nuclear reactors and nuclear atomic bombs and that kind of stuff. Okay, that's why they use those type of elements for those situations. Every exponential growth or decay model is going to work off of this setup. If we do this the first time, we're not going to have to do it every time. Y'all could write this on your cheat sheet, and you're going to have how this comes about being every time you need it. For any exponential growth or decay model, this is how it comes to be. It's just a separation of variables equation. All I'd have to do to solve that differential equation, this means the rate at which a population or something grows is, with respect to time, is proportional to that population. To separate this, what would I need to do? If this was a separation of variables question, what would I have to do to start off? Move the dt over, okay? So d sub n is k sub n dt, okay? Now, separate it. What needs to be done to separate stuff? Divide k in. I don't want to divide the k, just the n part, because you know it doesn't go over there with the t's. So divide by n. Oh, okay, I'm sorry. Sorry. So if I divide that n out of both sides, I get 1 over n dn equal to k dt. So am I ready to integrate? Y'all are confused because you don't see numbers, but it's still the same process. Okay? We're going to integrate both sides. What is the integral of 1 over n? Okay, on the right side, though, what is the integral of k with respect to t? kt plus. Now what do I want to do? E it. So that gives me big N equal to what? Constant 1 e to the kt. Now this equation you've got, this means this will be my population or my amount or whatever I'm looking for with respect to time. Time is what you plug in for t. K is your constant of proportionality, which you'll a lot of times have to find or be given to you. But let's look at one more other thing. Let's talk about at time equal to 0. Before the whole thing starts, before any of the process begins, before I put the little bacteria together in the same Petri dish. N equals C1. If I let T be 0, N would equal just C1. Actually, that's true. What that would be is N, or C1, would equal my initial amount. How much you start off with. Your initial population or your initial amount. If I put 12 rabbits in a cage together, my n sub 0 would be 12. We know what happens when I do that, right? When I put 12 rabbits in the same cage together, those are going to multiply quickly, okay, with respect to time. So n sub 0 is your initial amount. So this is our model that you're going to use every time. N is equal to the initial amount times e to the kt. Now, you never have to do that again. We don't teach in Math 112 how to separate variables and integrate. We just give them these equations and tell them how to use it. Okay? So now you know how we got the equation. You may have seen a model like this before and you didn't realize it was the same thing. How many people remember this equation? Amount accrued is equal to P times e to the RT. PERT. That's the compound interest equation. That is this model. You're going to have a problem on the test next week that is just the compound interest question. All you got to do is get your cheat sheet out and look at this model and plug your information into it. That's all you got to do, okay? That's another example. And this works for growth or decay. What do you think is going to make, what do you think is going to be different about your equation if it's a decay problem instead of a growth problem? Your k is going to be a negative number. If it's growth, k will be a positive number. If it's decay, k will be a negative number. Okay? That's the difference in the situation. Good. So here's a couple of problems we want to do about exponential growth and decay. A culture initially has n sub 0 bacteria. They didn't even tell us how many it had. It could be 100 bacteria, it could be 1,000,000. We don't know. But n sub 0 bacteria. At 1 hour, the number of bacteria measured to be 3/2. That's more. It's increased 3/2 times its original amount. If the growth rate is proportional to the number of bacteria present, determine the time necessary for the number of bacteria to triple. How long is it going to take for the number of bacteria to triple? So let's see what we got here. At t equals, let's say my model was n. So on that first one, the initial amount we had was n sub 0. No time. Okay? At t equals 1, we had 3/2 n sub 0. How in the world can we solve for k then? Let's see, can I solve that equation for k right there? If I divide both sides by n sub 0, I get 3/2 equal to e to the k. How do you solve that equation? Natural log, yeah. To get rid of an e, you natural log, right? So natural log of 3/2 is equal to k. Give me a decimal on that if you don't care. Natural log of 3/2. Punch it in your calculator. We're going to do 4 decimal places. That'll give me a pretty accurate result. 4 decimal places on any of these fillings we do. 0.4055. Okay. So here's my equation now. The number present is equal to n sub, my initial amount, e to the 0.4055 t. There's the equation I used. Now, Look at the question. It says, if the rate, determine the time necessary for the number of bacteria to triple. So the amount we want, if we want it to triple, what amount will we have? 3 n sub 0, right? That would be triple the amount we started with. Equals n sub 0 e to the 0.4055t. Austin, you said just go ahead and just put 3, right? Did you say just 3? Oh, you did say it. Okay. But you see that the n sub zeros are going to divide out. So I wondered if you just went ahead and already saw that or something. So 3 equals e to the 0.4055. And use your algebra skills to solve that. What do we need to do? Natural log of 3 equals 0.4055t. Divide by that decimal, and you should have it. So approximately how much time does it take to triple my number of bacteria? Yeah, 2.7 hours. Put that note in there so you know where that equation came from. Questions about that? Every time I work a growth and decay problem now, I'm going to use this method right here. I'm going to use this model to help me get started with it. Let's try another one. The number of bacteria in a culture increases at a rate proportional to the number of bacteria present at any time. That lets me know that it's that model. After 3 hours, it is observed that there are 400 bacteria present. At the end of 3 hours, there's 400 specimen of bacteria. So, 400 equals an initial amount we don't know, e to the k times 3. Next sentence says, after 10 hours, there are 2,000 bacteria present. So 2,000, still don't know how many we started off with, e to the k times 10 hours. So what I'm going to try to solve this equation for was the initial number of bacteria. We're trying to find n sub 0. Y'all agree with that? In both of these, n sub 0 will equal 400 divided by e to the 3k. In this one, n sub 0 would be 2,000 divided by e to the 10k. But what do we know about that? Set them equal to each other because your initial amount is the same for both scenarios, right? N sub 0 is exactly the same for both scenarios. So here we got 400 over e to the 3k equal to 2,000 over e to the 10k, which I can cross multiply and give myself an equation. So let's see what we got there. 400 e to the 10k equals 2,000 e to the 3k. Any suggestions, guys, on how I might solve this? Divide by e to the 3k. What else can I divide by? 400. Okay, so what's it going to give me on the left side? $400 into 2,000. Is it just 5? Yeah. Those cancel out. E to the 7k equals 5. How am I going to solve for k? Good job. Natural log both sides. Divide by 7, good. 4 decimal places will be sufficient. ln of 5 divided by 7. Yeah, 0.2299. Well, what do I need to do then to find n sub 0? Either one, it didn't matter, right? You could do it to both to make sure you're on the right track, okay? So let's go ahead and do 400 divided by 3 times, I'm going to use, how do I want to do that? I may have to do some parentheses stuff here to get this right. 400 divided by, open parentheses, 3 times 0.2299, close parentheses, E, on my calculator, y'all might have better calculators than me, equals. Tell me what y'all get. $200.69 is what I got also. Did y'all get that? But still, if you were reporting, if you were a biologist, some kind of scientist working in this lab, whatever, what would you report as your initial amount? 201 or 200, somewhere around a closer, even, nice number. I think I put 201 as the answer, but we're just going to put 200. How about that? Of course, you're not going to put a decimal answer on this. Don't put a decimal answer because we don't care about how many little half bacteria are laying around in that petri dish. Okay? How is this? Is this easy? Y'all are doing a whole lot of EN and LN and working with your logarithms. I love logarithms. It's my favorite thing to teach in pre-cal days. All right, let's do one more of those. Questions on any of this so far? Stop me if we don't know what we're doing. Oh, we got some decay going on this one. It says the radioactive isotope of lead, lead-209, decays at a rate proportional to the amount present at any time and has a half-life of 3.3 hours. The fact about the proportional to the amount present at any time tells me that that's going to be the same model. The amount we started off with, or that we have at any time, equals the initial amount times e to the kt power. Same model. This time my k is going to be negative when I solve because it's the decay issue. Half-life is 3.3 hours. What does half-life mean? Right? But for them to call it a half-life, half of it goes away. The time required for half of it to decay. So if I put a pound of plutonium on the desk here, whenever I have a half pound left, that's where we can mark the half-life. If you went over to the chemistry lab over here, she's going to have a book probably about this thick of elements and information about them, and you can look up half-lives on about any kind of known element that you want to. Okay? That's all published information. But this has a half-life of 3.3 hours. If 1 gram of lead is present initially, how long will it take for 90% of the lead to decay? Okay, so we got to get some information to start off with. Let's work with the half-life first. If we started off with 1 gram, how much would I have after half of it's gone? 0.5? N sub 0 was 1. We know that. 1 gram. Times e to the k times, what's the time on that for the half-life? 3.3. Okay. That's enough for me to get the answer, isn't it? I can solve for k just from that right there. .5 is equal to e to the 3.3k. So what do I need to do here? And divide by 3.3. If you don't get a negative, you've done something wrong. So what y'all get for k? I told y'all to take 4 decimal places, but if you take 4 decimal places, it's 0, 0. So we'll just leave it like that. Okay? So here's my model. N equals N sub 0 e to the negative 0.21 t. If 1 gram of lead is present initially, how long will it take for 90% of the lead to decay? So if 90% is gone, how much is left? 1/10. Y'all agree with that? 1/10 of a gram. So 0.1 equals 1 e to the negative 0.21 t. So we're solving for t here. Again, it's going to be natural log of 0.1. How many hours? $10.96. What can we do? What can we do? It's actually a good bit more than 10, so we'll just go with 11 on that one. Yeah. You know, I just been doing these problems like I knew what I was doing. Let me check myself real quick. Okay, Grant, make sure I had done something down that I didn't remember. We are cooking with gas. Yeah. Yeah. K is going to be your rate of proportionality, whether it's growth or decay. What would your rate be in a money situation? Interest rate. Whatever your interest rate is, going to be the rate that you use. In these, continuously compounded interest. I already showed you this. I'm not going to separate those variables and do all that for you. It's the same situation. Normally we would have n equals to n sub 0 e to the kt. But when a money situation comes into play, y'all need to put this. Your amount present at any time is your principal. Principal means the amount of money you start with. So n sub 0 is the same thing as initial amount, right? Times e to the rt. It's spelled the same way as the school principal. That's the initial amount of money. R is going to be a percentage that you need to change to a decimal. And time is years. continual interest. Make sure this little formula is on your cheat sheet. This will be a gimme question. 8 points in your favor right here. Find the amount of money accrued at the end of 5 years when $5,000 is deposited in a savings account, drawing 5 3/4% annual interest compounded continuously. So the amount, what is your principal? $5,000. E to the, what was your interest rate? How do we need to put that? 5 3/4. What's another way we could talk about that? Yeah, what would that be? So y'all know 5 3/4 is 5.75, right? Is that the same thing as 3/4? The same thing as 0.75? And so also you said move the decimal back to the right, to the left. I mean 2 places to the left on that. So it'd be 0.0575 be your interest rate times your time, which was how many years? 5 years. So you got to do a little arithmetic first on this one. Multiply that out. 0.0575 times 5. And I get 0.28. So you should be able to just approximate that. On this, we want to round to the nearest cent because it's money. Round to the nearest cent. You want 5,000 times e to the 0.2875. $6,665 and how many cents? 45. So what if I want to be a smarty pants and say, how much interest did you earn? How could you calculate how much interest you earned? Subtract how much you put in there. Subtract your 5,000, right? So you earned what, about nearly $1,700 in interest on that account in 5 years. Started out with 5,000. At the end of 5 years, now you got $6,665.45. Okay, let's take a 10-minute break. Y'all been going about an hour and 10 minutes, so we'll take us a little break and come back and work on this. Every application we've looked at so far has required separation of variables to solve, which again is our most low-level skill we've got, except just straight out integration. But separation of variables is kind of that way anyway. Integration is all that's involved. This is also another example of separable equations. You could also, I think, use integrating factors on this one, but I'm going to do it with separation of variables. Newton's law of cooling states that the rate at which the temperature changes in a cooling body is proportional. That's going to be your K right there when they have that word in there, proportionality or proportional, to the difference between the temperature in the body and the constant temperature ambient or surrounding medium. For example, if I took a cake out of the oven and I set it in this room, which the air conditioners work pretty good right now, if I took a cake out of the oven, we're saying that cake's probably like 350 degrees or so, okay? And I sat down here on this desk. If this room is around 72, 75 degrees, how long is it going to take before the cake becomes 72 degrees? Okay? That is the kind of situation that you're looking at with Newton's law of cooling. This is the model you need to write down. This is the one that you're going to use on all the cooling problems. D big T over D little t. Those are two different T's. The big T stands for temperature. The little t stands for time. K is a constant of proportionality. T sub S means the surrounding medium, or in some books you might hear this called the ambient temperature. When a cake is removed from a baking oven, its temperature is 300 degrees Fahrenheit. 3 minutes later, its temperature is 200 degrees Fahrenheit. How long will it take to cool the cake to cool off to a room temperature of 70 degrees Fahrenheit? So they're saying that the temperature in the room is 70. That's your T sub S. Okay? So, if I know my model here, dt over d little t is equal to k times the temperature of the cake at any time, t, minus, in this case, 70. 70 would be my ambient temperature. First thing I need to do is multiply both sides by dt, d little t. To separate, what do I need to do, guys? So 1 over big T minus 70 is equal to K dt. Integrate both sides. I don't have any room in this one, so get all I can out of this. What's the integral of 1 over T minus 70 going to be? ln of t minus 70 equals the integral of k with respect to t. So if I e both sides, t minus 70 will equal c1 e to the kt. Another thing I could do is go ahead and add 70 over. So I've got a better looking. I need to find K next. So what I'm going to do is use that next sentence given to me. We used the 300 part. Well, no, we haven't used that yet at all, have we? At time equals 0, at time equal to 0, the temperature was 300 degrees Fahrenheit, right? C1 e to the 0, it's just going to go away, isn't it? If I plug in little t equal to 0 right there, that's going to be e to the 0, which is 1. So C1 plus 70. So what's C1 equal to? 230. So now my model says this. T equals 230 e to the kt plus 70. Our model's getting better looking all the time. Next statement. 3 minutes later, the temperature is 200 degrees Fahrenheit. 200. So 200. Let me put a little note here for you when you go back and look at this, so you'll say, where is he getting all that? At T equals 3. 200 is the temperature. If I don't run out of room here. Okay? I want to solve this equation for K. Algebraically, what I need to do here. Subtract 70 from both sides, so that's 130 equals 230 e to the 3k. Up here in my third column. Divide by 230 on both sides, I'd get 13 over 23 equal to e to the 3k. LN both sides. So 13 over 23, you want to LN that, and then divide by 3. Why do you think I get a negative K? Cooling. Good. 4 decimal places. 1902. I think that's what I guess what I got. Y'all check on me on that. Okay. So here's my model again. My better model. T is equal to 230 e to the negative 0.1902 t plus 70. So now I'm ready to answer my question. All that work was just getting my model set up, okay? We need an actual answer to the question now. So, how long will it take the room cake to cool off to a temperature of 70? Plug in 70 for T and solve it for little t, right? There's a problem with it though, guys. Theory here. Problem with solving that. If I plug the 70 in right here, those 70s are going to get 0. You're going to divide by 230, it's going to get 0. Nothing, E is never going to equal 0. E to the power of anything never going to equal 0. Because if you think about it, you won't be able to solve this. If you think about it, how long does that take going to remain 70 degrees? Forever. When it gets 70 degrees, it's going to stay 70 degrees. Y'all agree with that? If it cools down to room temperature, if it's still sitting in that room, it's going to be 70 degrees for a long time. So a trillion minutes or seconds, or whatever that minutes, going over the minutes from that time, it's going to be 70 degrees. So to make this work out, we can't get it equal to 0. What do you think we should do? We go a little bit higher than 70. How about 70.71 would be good? That'd be getting close there, 71 degrees. Or we could do like 70.1. How about that? You want to try that? So that's not quite 70, but it's just right there above it. So 70.1. Let's try this. Which would give me 0.1. If I divide that by 230, 0.1 divided by 230, then I'm going to LN it, and divide by my power. Divide by 0.1902 negative equals. Yeah, that's real close to what I got earlier. Tell me what y'all get. it's going to take approximately like 40 minutes, 41 minutes. Not that much difference between 70 and 70.1. Well, let's try something while we're on this screen. Let's just try something. Instead of saying 70.1, let's try 70.001. See what kind of difference that makes. 70.001. Let's see if that makes any difference. So 0.001 divided by 230. LN that and divide by 0.1902 negative. Look at that. 64 minutes. That's a lot of difference, isn't it? So why can I not? Can you see why I cannot use 70? Okay. So that's not a good question if you ask me. As time approaches infinity, 70 degrees is what you would. If your ambient temperature is there, that's what's going to always get closer and closer to. Yep. Not zero in on a specific time when that happens. You can't. Well, it's kind of like an asymptote. You get closer and closer and never touch it, right? This will be an asymptote there at that 70. It's like you get closer and closer and never actually touch. So what is the instantaneous time where that measures exactly 70 degrees? I don't think you can solve it in the equation. Yeah. But at 70.1, you know you're getting really close. Okay. Let's do another one. Thermometer is taken from a room where the air temperature is 70 degrees. To the outside where the temperature is 10 degrees. We're talking about wintertime somewhere here, right? 70 degrees in the house, outside the temperature is 10 degrees Fahrenheit. After a half minute, the thermometer reads 50 degrees Fahrenheit. What is the reading at 1 minute? Then how long will it take the thermometer to reach 15 degrees? See, this one's a possibility. Why? Right, you're not asking when the temperature is going to be 10. When it's going to turn to the same temperature to outside. It's 15 still above that, right? So this is way more calculable than the other experiment. So here is our model again. And this one you kind of have to repeat yourself a lot on because there's lots of stuff you have to find. That's why. So on this one, dt over d little t equals K times temperature minus the ambient temperature. What's the ambient temperature here? Where you're going into your cooling situation, what's your outside surrounding temperature? 10. T minus 10. So if I separate everything out, you guys might figure out some shortcuts you can do with this model so you don't have to do all these steps. Divide. Integrate. Natural log of t minus 10. And then the integration of k will just be kt plus c. Yeah, I could have modeled that last example on this. Y'all might could put something on your cheat sheet that would help you do change a lot of these steps out. So e both sides, t minus 10 equals c1 e to the kt. So I could actually add the 10 back over. First thing you want to talk about is an initial. The initial before anything happens. So if the initial at time equal to 0, you get, what was the temperature at time equals 0, by the way? 70? The thermometer read 70 at the initial point. So that's going to be C1 plus 10. So what's C1? 60. Remember, if you put in 0 right there, that becomes 1. So C1 plus 10. So here's my model update. 60 e to the kt plus 10. Update. After 1/2 of a minute, the thermometer reads 50 degrees Fahrenheit. So my temperature is 50. So I'm going to put that's 1/2 a minute. I'm going to put 0.5 K plus 10. So I'm going to be able to solve for my K this time. Subtract 10 and I get 40 equal to 60 e to the 0.5 K. Divide by 60, that's going to give me 2/3. ln of 2/3, by the way. Natural log of 2/3 divided by 0.5. Why do you think that's kind of a large number, that constant? Yeah, it's cold outside. It's cold outside. I skipped some steps there. Do I need to go back to it, any of it? Right here, I divided the 60, so 40 over 60 gives me the 2/3. 2/3 equals e to the 0.5 K, so to get rid of the e, I ln to both sides. Update your model. Temperature is equal to 60 e to the negative 0.8109 T plus 10. So your model is complete now. So look at these two questions. I'm going to name one of these questions. What is the reading at T equals 1 minute? I'm going to say that's question A. And how long will it take the thermometer to reach 15 degrees? I'm going to call that question B. Let's see if I have any room. Yay. I do. So next page. My model is 60 e to the negative plus 10. Okay? So A part at T equals 1. If I plug in 1 in there, that's going to be negative 0.8109 plus 10. So that's just a calculator problem. Just a calculator problem. So let's see here. 0.8109 negative E times 60 plus 10. What'd y'all get? Okay. So B question says, how long is it going to take for it to cool the thermometer to read 15 degrees? To read 15. So that's going to be 15 equals 60 e to the negative 0.8109 T plus 10. So you're just going to solve for T here. How long? How much time? Subtract 10 from both sides, you get 5. Divide by 60, you get 1/12. LN both sides. So divide by that. T would be approximately 1/12 ln divided by 0.8109 negative. What y'all got on that? 3.06. I'll say 3.1 approximately minutes. If you get your model set up right, then you can answer questions about it. But you got to get that part set first. Yes, sir. Same thing. Okay. It's going to add. Mm-hmm. Just like just the basic arithmetic of it. Sure will. It's going to make it actually when you get your model thing, you'll have a minus over there instead of a plus. That'll be like minus on that course. So take it away, make it better. Yeah. If you had a negative temperature, it'd be the same.
Is that going through all that vertical area? Just make a model easy for it.
What do you got? Does that work every single? Is that what it looks like every single time? Let me write that down. I'm not going to endorse it because I had it myself try to play around with it, and that's what tells it anyway.
C is equal to parentheses C minus TS. E decay.
Just like
E decay.
plus T. Yes. He's saying that model is working on all the two problems out there. Might be helpful. Don't look at that. I don't know that you would find that published, but if you're seeing in the two problems we've worked, I agree with you. It's like you're seeing the same steps over and over. Okay. This next concept, guys, we're going to get to review linear equations. I told you there's going to be several problems on the test next week, solving linear equations. And remember, to solve the first order linear DEs, you need an integrating factor. That's what you use to solve them. I'm as dumb as a hoe handle when it comes to stuff like this. If you guys have done your physics and stuff already and know about circuits and electricity, if you know that stuff, give yourself a clap and a pat on the back. I am so dumb about this stuff. How many of y'all did electronics? Anybody work with that a little bit? So you're kind of familiar with this stuff? I know nothing about it. I've actually thought about taking one of those little courses so I'll make myself look smarter. I know how to do the math. I'm going to show you how to do the math on this. I know how to do that. But actually understanding what a circuit actually does and what it is, I'm clueless. Okay? So if you guys take this class in engineering school, know you're probably going to see this setup, and your teachers, what you were supposed to get from this class is how to work the math part of it. Okay? So you're going to get that with me. In this problem, there's a difference between these two types of circuits. This is an LR series circuit. In a series circuit containing only a resistor and an inductor, Kirchhoff's second law states that the sum of the voltage drop across the inductor and the voltage drop across the resistor. See, I remember like Ohm's law or something like that. I've seen that before. I know this. I've heard these words before. Is the same as the impressed voltage E of t on the circuit. Thus, we obtain the linear differential equation for the current I of t. So here's a linear equation. You would put those values or whatever in their correct respective places. L and R are constants known as the inductance and the resistance, respectively. The current, which is I of t, is sometimes called, that should be V, not T. response of the system. The response of the system. So an LR series, this is your setup here. The RC series circuit, voltage drop across a capacitor with capacitance C is given by Q of T divided by C, where Q is the charge on the capacitor. Hence, for the series circuit shown, Kirchhoff's second law gives this equation. Resistance times I plus 1 over C Q equals E of T. Current I and charge Q are related. Look at this. It says current, which is I, is the derivative of Q with respect to T. I want you to come back to this in just a second. With the problem I'm going to show you, we're going to come back to that rule in just a second. So the former DE becomes the linear differential. This is the model we're going to look at right here. Now, I can look at that and put numbers where they're supposed to go, but just understanding the mechanics behind all of it, I don't really know and couldn't explain it to you. I know we're going to plug a number in for this R, which is your resistance, whatever they give you. I know you're going to plug in a number for this C, capacitance, and you find E of T, which, what do we call that? Voltage. Impressed voltage, yeah, E of T. So let's look at a problem and see if we make any sense out of that. A 100-volt electromotive force is applied to an RC series circuit in which the resistance is 200 ohms, the capacitance is 10 to the minus fourth power farad. Find the charge, find Q of T on the capacitor if Q of 0 equals 0, and it says then find the current I of T. So we'll call this question A and B. Do I have any space? Yes. Good. Okay. So the model that we had on the last page, R dq dt plus 1 over C Q equals E of T. That's our model that we're going by here. Okay, so the 100-volt electromotive force, that goes where? What's the 100-volt? What's the electromotive force? Which one of those things you're going to plug in with the 100? E of T will be 100. Yeah, that's your electromotive force. Resistance is 200 ohms, so I'm going to put 200 there. Capacitance, it's 1 over 10 to the negative fourth. So 1 over 10 to the negative fourth Q. What could I do there to make that a little bit make sense? 1 over 10 to the minus fourth, what would that be the same thing as? 10 to the fourth. So let's go ahead and fix that. 1 over 10 to the minus fourth would be 10 to the fourth, or 10,000 Q. Equal to, y'all said 100 for that. So I have a linear equation, guys. Y'all remember that? How to solve a linear differential equation? You got your derivative, you got your Q right there, and then this has no Q involved in it at all. That's the linear setup. We're going to use the integrating factor model and how to solve this differential equation. What's our first step going to be? You don't want your constant on your derivative, so you're going to divide through by 200. $10,000 divided by 200. $50. 100 divided by 200 is 1/2. Okay, so integrating factor. This is going to be a review of how to do these. Your integrating factor, remember I called it I of x, is e to the integral power of what in this problem? 50. Look at y'all. Good job. So what's that going to be? Okay, nope. 50 e to the 50. In this case, guys, it's not going to be x. What's your variable? T. It's going to be with respect to time. So e to the 50t. If you did 50x, you'd probably still get out of it. 50t. E to the 50t. So if I multiply both sides by the integrating factor, if you remember this, the left side just comes out to be the integrating factor, e to the 50t times q prime. Y'all remember that? Every time. If you do your integrating factor right, that's what you should have. So now I do what? Integrate both sides. Good job. So e to the 50t times q equals. Okay. I love these because it makes us have to think about our arithmetic. What? Good deal. Look, e to the 50t, your u is 50t. du would be 50. We have to compensate with the reciprocal. Y'all remember that? So 1/2 times 1 over 50 will be 1 over 100. 1 over 100 e to the u, which is still 50t, plus c. Okay, so what's q? Divided through by e to the 50t, right? So you get 1 over 100 plus c1 e to the negative 50t. And there's our solution. The only thing that we don't have, though, and I need to go ahead and fix, I'm going to go to the next page and do this, but they gave us an initial value. Did y'all see that? Q of 0 equals 0. This is not doing good. Okay, Q of 0 equals 0. So 0 equals 1 over 100 plus C1, right? So what's C1 equal to? So Q of t is actually 1 over 100 minus 1 over 100 e to the minus 50 t. Is that all we were supposed to find? Yeah. A part says find the charge Q of t on the capacitor if Q of 0 equals 0. So this is the answer to A part. That's the total answer to A part on that one. Now, if you look at it, B part said find what? The current, which was given by the function I of t. What? I told y'all to circle this a minute ago. I is equal to dq over dt. He's exactly right. What does dq over dt mean? Changing q with respect to time. What is changing in? What does that mean? Who just said that? Q prime. It's the derivative. It changes the derivative. You're right. Change of q with respect to time. But, oh, what is q? What is q? What do we call it? Okay. But this little circle part here where it says that I is the derivative of q with respect to t, all we got to do to find I of t is take the derivative of q. Okay? So let's do that. I of t is dq over dt. So can we switch our brains around a little bit here? See if y'all can remember how to do this. We're having to do derivatives. What? You're probably right. Look at this. What's the derivative of 1 over 100? 0, so skip on over here. Negative 100 times the derivative of this. It's e to the minus 50t times, the chain rule says it's e to the u times derivative of u, right? So it's going to be negative 100 e to the negative 50t times the derivative of negative 50t, which is negative 50. That's what you were saying, Austin. 50 over 100 is what? 1/2 e to the negative 50t. That is the I of t function. Okay, I did all that work, and all I wanted you to get out of that was how to solve a differential equation using an integrating factor linear equation, okay? Let's practice at that. There will not be a question on the test from circuits, period. There will not be a question ever on the test that I give about circuits. But I showed you one. So if you guys have a class where you have to do this stuff, go back and look at these notes, see if that'll help you. Don't throw nothing you get in here away. Okay. Now, this is fun. We got 2 more I want to do. This is the last application I want to teach. And I've got a couple of examples of it. This is, to me, this is still going to be linear again. We're going to practice that some more. But this is kind of neat. I like stuff that I can visualize and kind of get an idea of what's going on. This will make sense to everybody. Okay? Mixing solutions together. Initially, 50 pounds of salt is dissolved in a large tank holding 300 gallons of water. So y'all got a picture of that, what that would look like. They've got this 300 gallons of water, and they just got a 50-pound bag of salt that they threw in there and mixed it all up. So you got a salt water solution going on. Then we're going to start pumping something in. So initially, we've got 50 pounds of salt, 300 gallons of water, period. Does that change the volume of how much liquid's in there, adding the salt? Does it really? If you mix it together, you still kind of got 300 gallons of stuff. It's kind of how it would work. A brine solution is then pumped into the tank at a rate of 3 gallons per minute. And the well-stirred solution is then pumped out of the tank at the same rate. So at the same time, we're going to start pumping salt water in at a rate of 3 gallons per minute and out of the tank at 3 gallons per minute. So you got this water, just mixture going, and it's coming in at one rate and going out at the same rate. Okay? If the concentration of the solution entering is 2 pounds of salt per gallon, determine the amount of salt in the tank at any time. A model for the amount of salt in the tank at any time. How much salt is present after 50 minutes of this activity. And then How much salt is present after a long time? How long is a long time, right? Well, let's look and see what happens here. This is your model. So on your notes, when you're making your cheat sheet out, your notes, the model you want to follow for mixing problems is the amount of salt, we're going to call it Q, is equal to the rate entering, the rate of salt entering, call that one thing, minus the rate of salt leaving. Oh, I got plenty of red. Okay. There's your model. The amount of salt is given by Q of T. At any time T. Okay, so let's look at this problem here. dq over dt. We're going to look at this specific problem. The rate of salt entering, okay? It says a brine solution is pumped into the tank at a rate of 3 gallons per minute. So let's put that first. 3 gallons per minute. What's the concentration of that? How many pounds of salt per gallon? The solution, concentration of the solution entering is 2 pounds per gallon. So 2 pounds. So that's how salt, the rate that salt is entering into the tank. So as you guys can see there, some algebra takes place. Gallons cancel out. So 6 pounds of salt per minute in that part right there. 6 pounds of salt per minute entering into the tank. Minus, it says that it is pumped out at the same rate. So the rate is 3 gallons per minute again. But the concentration is going to be different. Don't y'all agree? That was exactly though how it was when it started, before any pumping started happening. 50 pounds of salt in there, 300 gallons of water in there, but that's before any pumping started taking place. So when the pumping starts taking place, we don't know how much salt. We have zero idea about salt. So we're just going to call it the amount of salt, Q. In how many gallons? 300 gallons. The rate leaving is just going to be some mixture of salt out of 300 gallons of water. We don't have any idea how much. Okay? So seeing that algebraically also. So that's going to make our model. dq over dt equals 6 minus, what about the 300? How's that going to reduce? dq over dt equals 6 minus 100 over q, 1 over 100 q. Is that a linear equation? Could that be represented as a first order linear equation? I need to move stuff around, don't I? What do I need to move? How do I need to fix it? Other side. So let's go ahead and do that. Let's go to the next page. Y'all were talking about the, Austin said something about the 50 pounds of salt, 300 gallons of water. We're going to use that for our initial value. Okay, at time equals 0. At time equals 0. So dq over dt plus 1 over 100 q equals 6 What's my integrating factor? E to the integral of 1 over 100. So e to the what? One over 100 t. You're right, though. I mean, but the variable's t for time here. Multiply both sides by the integrating factor. Y'all might think this is a bunch of writing for no reason, and it may be. Y'all can probably shorten it down yourself. If I multiply that by both sides, that's what you'll have. On the left, we know we get the derivative of the product. Integrate both sides. I'm going to let you guys help me on the right side. Your u would be 1 over 100, right? 1 over 100 t. du would be 1 over 100. Compensation would be 100 times the 6. So 600 e to the u, so e to the 1 over 100 t plus c. So q would equal what? I'm going to do it negative instead this time. You said c over, so that's the same thing as having a negative power, right? Okay. I almost got it. My model's not complete because I have a c in there. So let's talk about the initial value. At time equal to 0, how much salt? There was 50 pounds of salt at time equal to 0. So Q would equal 600 plus, 50 equals 600 plus C1 e to the 0, right? So what's C1 equal to? So my model now is complete. Q of t would be 600 minus 550 e to the negative 1 over 100 t. I think that's the answer to A part. Let's go back to our question. What did the A part question ask us? If the concentration of the solution entering is 2 pounds per gallon, determine the amount of salt in the tank at any time. So here's a question. I'll put it in red so we see it. How much salt is present after 50 minutes? So that's going to be B. And C is after a long time. Q of t, we found that answer to A. That means you can find out how much salt's in the tank at any time t. Okay? How much salt is present in the tank after 50 minutes of pumping? 50 minutes of pumping. So we're just going to plug in 50 here. $600 minus 550 e to the what? What is negative 100? Well, I'll just go ahead and write it in so y'all can see what I'm talking about. 50 times negative 100, 1/100th would be negative 1/2. So get me an approximation there. Use your calculator. 600 minus 550 times 0.5 negative E equals. Y'all tell me what y'all get. How are you going to answer in units here? Pounds of salt in the tank at 50 minutes of pumping. How much salt was in there in the beginning? 50 pounds. Now, after 50 minutes of pumping, you got 266 pounds of salt in there. How is there more salt? What are you pumping in there? You're pumping a brine, right, which is salt water. You're pumping the salt solution in there. So C part is my favorite part of this entire question because I teach Calculus 2 here. I love it. It says how much salt is going to be in the tank after a long time. So we can look at a limit concept on this. The limit as time approaches infinity. Y'all knew what a long time was. Look at that. Look at that. Look at that. The limit as t approaches infinity for 600 minus 550 e to the negative 1/100t. Now, it shouldn't take y'all very long, but it just depends on if y'all remember how to do this. If I plug infinity into this, I can't plug infinity into 600. No, can't do that. So this is going to be e to the negative 1/100 times infinity to make it negative infinity. E to the negative infinity would go where? If we have a negative exponent, where does it go? Down below. So you're going to have 550 over infinity. What happens, guys, in calculus 1, 2, and 3? What happens if you have a number over infinity? 0. So as time goes, you got 600 minus 0. So after a long time, what's the max of salt we're going to ever have? 600 pounds of salt in the tank is going to be your maximum amount of salt if that just keeps running forever. Absolutely. That was one of our rules we learned in Cal 2. If you have e to the negative infinity, right? So a number over infinity is going to be 0. There we go. Okay. Let's do one more problem. I know y'all are getting glazed over a little bit. Let's do one more. We'll have a little short break, and we'll finish it up. How about that? Sound good to y'all? This is another pumping question. Mixture problems. And this one, bites. This one's tough. Okay? So we're going to really get our thinking caps on and try to think our way through this situation. A tank originally contains 100 gallons of fresh water, no salt. Then water containing a ½ pound of salt per gallon is pumped into the tank at a rate of 2 gallons per minute. The mixture is allowed to leave at that same rate. After 10 minutes, the process is stopped. So phase 1 is over. All that happens for 10 minutes and then we stop, okay? Then it says, and fresh water is poured into the tank at a rate of 2 gallons per minute, with the mixture leaving again at the same rate. Find the amount of salt in the tank at the end of an additional 10 minutes, okay? So we've got 100 gallons of fresh water. We're going to start pumping salt water into it. We're going to do that for 10 minutes. We're going to stop. Then we're going to start pumping fresh water into it. So we want to know how much salt is still going to be left in there 10 minutes after we start pumping the fresh water into it. Are y'all intrigued? We're going to do 2 phases. 2 phases. That problem I just got through doing, test question. When we just got through doing, test question, just like it. This one, not so much. Parts of it, yeah, will be beneficial, but I'm not going to make it that hard for you, okay? This one's a hard one, but I want you to see the mechanics behind it, how it works. So, dq over dt equals the rate that it's entering, okay? So when we start pumping this stuff, water containing 1/2 pound of salt per gallon. So 1/2 pound per gallon is pumped into the tank at a rate of 2 gallons per minute. So 2 gallons per minute, that's the rate we're pumping it in there. Minus the rate leaving, it's allowed to leave at the same rate. So here's the thing. We don't know how much salt has been pumped in there. So it's some amount Q, we have no idea. And how much water? The tank was only holding 100 gallons. Some amount of salt in 100 gallons of water. We don't know. But it's leaving at the same rate, so it's going to be 2 gallons per minute, just the same as that one was. So do your algebra stuff here. Those 2's cancel out. I like that. Gallons and gallons cancel out. 2 and 100 are going to cancel a little bit. So let's see what we got here. dq over dt is equal to 1 minus 1/50th Q. Now to get that in linear form, I need to actually manipulate it a little bit. My integrating factor, either the integral of 1 over 50, what would that be? 1/50th t, multiply both sides by that. Of course, 1 times 1 over 50, we're just either the 1 over 150, I can't even talk anymore. 1 times that is just going to be that. So that's e to the 1/50th t times q prime equal to e to the 1/50th t. Integrate both sides. What's the integral going to be on the right side? Good job. Plus C. So my Q is equal to what? If I divide out that e to the 1/50th t out, 50 plus C1 e to the negative 1/50th t. Okay? So before we started pumping any salt in there or whatever, at time equals 0, how much salt was in the tank? Read the first sentence. A tank originally contains 100 gallons of fresh water. That means there's no salt present at time equal to 0. Okay? So Q is equal to 0 at time equal to 0. 0 equals 50 plus C1. So what's C1 equal to? So Q of T is 50 minus 50 e to the negative 1/50th t. There's my model. That's the model there. Now here's a question. How long did we let that happen? Phase 1. How long did phase 1 take place? After 10 minutes, the process is stopped. So at the end of this 10 minutes, how much ever salt I've got will be the amount of salt present at the beginning of phase 2. Does that make sense? It's going to be your initial value for the phase 2 problem. So let's go back here and do one more thing. After 10 minutes, if I plug 10 in for T, that's going to make that negative 1/5. Okay, salt present. End of phase 1, which equals the beginning of phase 2. I'm going to come back to this in just a second, okay? Phase 2. I'm going to stop the process. Now we're going to start something different. Fresh water is poured into the tank at a rate of 2 gallons per minute. Fresh water is going to start being pumped in. No salt. So 0 pounds per gallon times 2 gallons per minute. So the rate of salt entering is going to end up being what? 0 on this one. It's going to be an easier equation to solve too, by the way. A lot easier. But there's already some salt in the tank, so when it's coming out the other side, when it's leaving, there's going to be some salt coming out. Y'all agree with that? So minus Is it leaving at the same rate? Make sure leaving at the same rate. Okay. So same setup here. We don't know how much salt. Q pounds per, how many gallons was it? 200. Leaving it 2 gallons per minute. Okay. It was 100. Easy to fix. Okay, so dq over dt, that's 0. So it's negative 2 over 100 is 1/50th. Guys, is this a linear equation now? Or could it be separable? I could separate that one, couldn't I? I don't have to do linear on this one. I can separate it. So I could say that dt on both sides. I need to separate, divide the q on both sides. Integrate both sides. What's 1 over q dq? What's the integral of negative 1 over 50 with respect to t? What do I need to do now? E thing? Okay, so I've almost got my model set up. I've still got a C1. So let's talk about that for a second. In phase 2, how much salt did we have at the beginning of this phase 2? How much salt did you have initially? Salt present at the end of phase 1 or the beginning of phase 2 was all this glop right here. 50 minus 50e to the negative 1/5. You can figure that out. You can punch that in the calculator and get a numerical answer on it. We're just going to leave it the way it is right now, okay? 50 minus 50e to the minus 1/5. So that'll be C1 right there. 0 for t, so it makes this go away. So here's your model. Q of t is equal to 50 minus 50e to the minus 1/5 times e to the negative 1 over 50 t. There's my model right there. So the question for this problem, see if I can find it here. What was the question they were asking me in the whole mess of everything? Find the amount of salt in the tank at the end of an additional 10 minutes. So at 10 minutes after phase 2 begins, how much salt have I got? So what do I need to do? Yep. So if I plug in 10 there, it's going to be e to the negative 1/5 again. Let's get an approximation on that. I'm going to use my calculator here. In parentheses, I got 50 minus 50 times 1/5 negative E, close parenthesis, times 1/5 negative E equals. Okay, I got that. I remember this answer from the past, so tell me what y'all get when you get one, or if you get one. What would be units here? Why so little? You had fresh water to start with, and you just did the mixing process for 10 minutes. Then what did you start doing? Putting fresh water back in, right? So you're concentrating all that. No matter what you put in, you're still overpowering it with water with no salt in it. Okay? So that finishes that lecture 5. That's all application. So like I said, we'll go back to this one. This first mixing problem is a great example of what you'll see on the test. There should be a problem or two on the homework set also that you could practice there, making sure you know how to do that. Same situation, I will give you a problem just like that situation. Not the same exact numbers, but situation. Okay, and like I said, I don't want to do all of this. We're just going to do half this week and finish it up next week. Do y'all want me to finish up, or do y'all want to break? We're getting glazed over. Okay? Do y'all need to get up? Let's take 5 minutes, a short break. Get up and walk around. Get out of here for a second. Okay? Go to the potty or whatever you need to do. I want you to be with me for the next few minutes so we finish this up. We make a transition, like I was saying. After that lesson, now we're switching gears. Everything we've done up to this point so far has been in process of solving a first order. Everything that you've solved yet has been a first order differential equation. Whether it was separation of variables, a homogeneous equation, an exact equation, or a linear, first order linear differential equation. All of those were first order. In fact, they just had a single first derivative in them. You do not have any processes in your brain so far of solving a higher order differential equation, which I mean by being like 2 derivatives in it or 3 derivatives in it or so on. We're going to start out talking about linear differential equations of higher order. Except in a few cases in which a first order DE can be solved, in general, nonlinear differential equations cannot be solved in terms of the familiar elementary functions. Consequently, in attempting to solve higher order differential equations, we shall confine our attention to linears. On one of the first lectures we did, I gave you some examples of equations that were either, and I asked you to tell me, are they linear equations or nonlinear equations? You can have derivatives all you want, but you can only have one term with a y in it. Everything else has to be x's, numbers, functions of x, or constants. Okay? And none of your derivatives can be raised to a power greater than 1. That keeps it all linear. Specifically, we will examine the method of solution of linear equations with constant coefficients, which means all of our coefficients are just going to be numerical. We shall see that our ability to solve a linear nth order differential equation with constant coefficient depends on our ability to solve an nth degree polynomial equation. Do y'all know how to solve something like this? You know how to solve it? What? Factoring? What else? Can I use to solve that? Quadratic formula? Completing the square? I'm just going to make something up here, okay? How do you solve that? You get a gold star for the night. Good job. She said synthetic division. Y'all remember that? The rational roots theorem. You try to get this decomposed down to an x squared. When you get down to an x squared, then you can factor or use quadratic formula. But you try to find all the numbers that would possibly work as roots for this. Well, we're going to review all that, okay? So good job for you. All right. To solve these higher order linear differential equations, you're going to use those methods to do it. Algebra. Stuff you learned in pre-cal algebra or algebra 2 in high school. Okay? Forms of single differential equations can serve as a mathematical model for diverse physical phenomena. Variations of the simple linear second-order differential equation appear in mathematical analysis of many problems in engineering, physics, chemistry, and even biology. Okay? So, let's look at a couple of higher-order differential equations and just play around with them just a little bit. Just kind of want to get our feet wet tonight. We're not going to do too much heavy lifting. It says, given that y equals c1 plus c2 cosine of x plus c3 sine of x is a 3-parameter family of solutions. Why do they say 3-parameter? 3 different constants. Good job. Of the solutions of the DE, y triple prime plus y prime equals 0 on the interval from negative infinity to infinity. So they're saying that this is your DE. This is the solution to it. They've already solved it for us. That's the solution. But find a member of that solution that satisfies these initial conditions or initial value. Y of pi equals 0. y prime of pi equals 2, and y double prime of pi equals negative 1. So this is an initial value problem. So I want to try to find C1, C2, and C3 here. So let's start off with the first one. It says y of pi equals 0. So let's try, here's y. Let's see what we can gather from that. If y of pi equals 0, 0 equals C1 plus C2 times cosine of pi plus C3 times sine of pi. Now, depending on how your trig is, let's see how that works for us. 0 equals C1. What is cosine of pi? Negative 1, so that's going to be minus C2. What is sine of pi, or sine of 180? 0. So that's going to become 0 right there. So my first equation tells me what? C1 minus C2 is equal to 0. What can you conclude from that? They equal each other. They're the same. C1 equals C2. So let's leave that alone and use it later. Use that fact later. Take the derivative of your function right here, y prime. What's the derivative of C1? 0. Okay, next term. The derivative of C2 cosine x. Negative sign. So negative C2 sine of x. Okay. And then the derivative of your third term. The derivative of sine is just cosine of x. Now they gave us an initial value here and said that y prime of pi equals 2. So 2 equals negative C2 sine of pi plus C3 cosine of pi. So help me out there. We said sine of pi was 0, didn't we? So, and cosine of pi, y'all said was negative 1. Okay, so what's C3 equal to? We got a solution there. C3 is equal to negative 2. Okay, one more deal then. Y double prime. Take the derivative of this right here. Y double prime. The derivative of that one's going to be minus C2 cosine x and the derivative of the C3 cosine would be minus C3 sine of x. And they told us that y double prime of pi is equal to negative 1. So negative 1. I could go ahead and put a negative 2 in for that C3, but I'm just going to do it the way it is. So that's going to be negative C2 cosine of pi minus C3 sine of pi, which we know goes to 0 anyway. So negative 1 equals cosine of pi, y'all said was negative 1, right? So times the negative makes it positive 1. It's positive C2. So look at what you got. C2 is equal to negative 1. If C2 equals negative 1, then what does C1 equal? So here's my answer. It says find a member of the family satisfying those initial conditions. So here's your answer to the member of the family. Y equals negative 1. Okay, C2 is minus 1. So minus cosine of x plus C3. C3 is minus 2. So minus 2 sine of x. That's your special member solution of that special initial value problem. Getting all your C's out. Now you do realize if I were to take y triple prime of this and add it to y prime of this, then I should get 0. Even with the constants in there, it shouldn't matter. It still should give me 0. Let's do a boundary value problem. Who remembers what I told y'all first or second class where I said what's the difference between an initial value problem and a boundary value problem? Do you remember that? Anybody remember that? There's an initial value problem. Look at all your points I gave you. Y of pi equals 0, y prime of pi equals 2, y double prime of pi equals 1, negative 1. That's the initial value problem. This one's a boundary value problem. What's the difference? Y of 0 equals 0, y prime of 1 equals 1. So different x values. Different x values makes it a boundary value problem instead of an initial value problem. Same concept though. Okay? Same concept. So let's start off with what we got here. This is a family of two-parameter family of solutions to this differential equation, y double prime plus y equals 0. On the interval from negative infinity to infinity, find a member of the family satisfying the boundary conditions y of 0 equals 0 and y prime of 1 equal to 1. So I'm going to start off with the y of 0 equal to 0. Negative 0 is just 0. So those are going to go away. So 0 equals C1 plus C2. C1 plus C2 is equal to 0. How can y'all relate that to me? C1 equal to negative C2, or we could say that they are opposites, right? C1 and C2 are going to be opposite signs. Opposite signs. Okay, let's take the derivative of that. Y prime then would equal C1 e to the x. That don't change. But C2 e to the minus x, that minus is going to come down and say minus C2 e to the minus x. Y prime of 1 equals 1. So 1 e to the first and e to the minus 1. I'm going to do this. I like kind of what Zeb said there. I'm going to solve this thing for instead of minus C2, I'm going to say that that's plus C1. Can I substitute that like that? If C1 is equal to negative C2, so that's going to be positive C1 right there. Factor out the C1, you got E plus E to the minus 1. So C1 is equal to what? One over E plus E to the minus 1. What? And I don't want to make the decimal or anything like that one just because it's just a pain. Let's leave it in its exact form. What would C2 then equal? That's a lot of writing, so I'm not going to write those out as your solution. But what would you do? How would you write this? I will. My special solution will be y equals. There's your C1. I put a minus between them because of the -1 on the C2. Everybody needs to understand that you could get a decimal approximation of what's in parentheses. You can figure that out. E plus e to the -1, and then the reciprocal of it. Okay, that's a boundary value problem, and these are examples of higher order differential equations. Now, what's going to happen as you solve higher order differential equations? They're going to be a combination of functions that are called linearly independent functions. In this situation, e to the x and e to the -x are an example of a linearly independent function. Cosine x, sine x, and 1 are examples of linearly independent functions. Your solutions are always going to be a conglomeration of all of these added together independent functions. Linearly independent functions. Linear dependence and linear independence. A set of functions is said to be linearly dependent on an interval I if there exist constants that are not all zero. So if it's the same thing and all you've done is just multiplied by a new constant, they're linearly dependent for every x in that interval. If the set of functions is not linearly dependent, then they're said to be linearly independent. In other words, two or more functions are said to be linearly independent when neither is a constant multiple of the other on that interval. There is a test we're going to learn on how to determine if functions are linearly dependent or linearly independent. We're going to work something here called a Wronskian. Wronski was a mathematician. He developed this process to determine whether functions were linearly independent or linearly dependent. As you can tell, it's a determinant. Do y'all remember how to work a determinant? A 2 by 2 or a 3 by 3? If you remember, 2 by 2s were real easy. Like if I had 2, 3, 4, 6, how do we do that? Y'all remember? Multiply that forward diagonal like that. 2 times 6, 12 minus. I could do that again if I wanted to, right? What's that? The determinant will be 0. How do we do a 3 by 3? You remember that? My Cal 3 people better remember it. What now?
You multiply each one of the contents. 1 times. Or you could rewrite it.
I do the cheater's method. You're talking about the really technical way of doing that. I don't even know if I know how to do this. I've done the cheater's way so many times that I don't even know if I know the expansion the other way. I just recopied the rows, the columns, 3, 2, like that. Remember? Multiply and add, and then you do the backwards ones and subtract. Y'all gonna do that? Okay. I'm not going to bore you with doing that problem, but I just want you to get the process. You develop the Wronskian with your functions that you got, and if you've got 3 functions, then you need to do a 3 by 3 matrix, a 3 by 3 determinant. If you have 2 functions, you need to do a 2 by 2 determinant. And though you get your columns by the function, the derivative, the second derivative, so on. That's how you set up a Wronskian. Suppose you have this 3 functions and at least n minus 1 derivatives. If the determinant is not equal to 0, if when you do the determinant and you don't get 0, then the functions are linearly independent. If you get 0, that means they are dependent. not equal to 0 is independent. Okay? Let's practice this. That's all we got left to do tonight. We're going to do 2 or 3 examples of this. Determine if these functions are linearly independent or linearly dependent. So on this one, I got 3 easy functions to do. 0, x, and e to the x. We want to see if those are linearly dependent of each other or independent. So here's my question. What's the first derivative of 0? First derivative of 0. What's the second derivative of 0? Okay. What's the first derivative of x? What's the second derivative of x? What's the derivative of e to the x? And the second derivative also, right? So there's my 3 by 3 determinant. I'm going to recopy. How do you know that? It is going to turn out to be 0. Are y'all learning something? Anybody taking linear algebra right now? Some of y'all taking that? Is there something with this corner being 0 that causes it? If any row or column are 0, by 0 every time. So this is going to all equal 0. Which what does that going to determine? Are these 3 functions going to be linearly dependent or independent? Dependent. If any column or any row, I haven't ever taught this. That's good information. I would have just shown you to do it out, not have known that. Good deal. Okay, look at this one. This is a little bit harder. Five cosine squared x, sine squared x. So we got 5. So the first derivative is 0, 0. Cosine squared of x. Now this is the hard part. Let's see how many of y'all people remember your calculus days. How do you take the derivative of sine squared x? It's the same thing as that, right? Sine squared x. So the derivative is going to be 2 out front times the derivative of inside. What's the derivative of sine? Does anybody know what that is? What that's the same thing as? It's sine of 2x. I'm going to replace that just because that's an identity, a double angle identity. I'm going to say that this is sine of 2x, the derivative is. It's going to help me with my math. That's one reason I want to do it. That's a double angle identity. 2 sine x cosine x is sine of 2x. What would the derivative of sine 2x be? Sine of 2x. It would be cosine of 2x times 2, right? This one, yes, sir. No, this one you wouldn't have a negative sign, right? 2 out front. Keep this like it is. To the first. Then times the derivative of the inside. That's the second one. No wonder y'all looking at me like I'm from Mars. Okay. Sine squared x, that's going to be this. Let's change all this. Sine of 2x. I messed up, guys. 2 cosine 2x. Sorry. Hopefully this is going to work out better. Let's see here. I know what you're talking about now, then. He wasn't paying a lick of attention to what I was talking about. That was me doing it wrong. Cosine of x squared would be how you treat that, right? So that's going to be 2 cosine x times the derivative of cosine x, you said right, negative sign. What's that going to be again? That's the same identity, isn't it? Except negative. It'll be negative sine of 2x. And then the derivative of that is going to be negative 2 cosine of 2x. Okay, so I'm going to do the long way here. Boring, boring, boring. Okay, diagonals. So that would give me negative 10 sine of 2x cosine 2x plus 0 plus 0. I like the 0 part. And now I'm going to do the backward diagonals in green. The first one, I'm going to go backwards. I'm going to do this one first. So that's 0. On this one, you got minus the same thing. Minus 10 sine 2x cosine 2x. And on this one, you got 0 again. Hallelujah. So what's that going to tell us? It's going to cancel out to what? Zero in that one. So what does that tell us? Linear dependent or linearly independent? Pop quiz. What's this determinant called? Wronskian. Wronskian. I think that sounds Polish to me. Wronski, maybe the last name, something like that. That's what you're finding. If I ask you to find a Ron, you'll have to do this later on something else we're talking about. The Wronskian is the determinant. Okay? One more and we'll be through. Hallelujah. E to the x, e to the minus x, and e to the 4x. We want to determine if those are linearly independent of each other or linearly dependent. The reason I'm doing this in the first place, when you're solving a higher order equation, all of your solutions should be a combination of all linearly independent functions. Okay? Every time. Before it will work. So let's see what this one turns out to be. E to the x, e to the minus x, e to the 4x. Derivative of e to the x is e to the x all the way down. Derivative of e to the minus x, negative e to the minus x, and positive e to the minus x. Derivative of e to the 4x is 4e to the 4x, and 16e to the 4x. Recopy. Guys, when you multiply like bases, what do you do with the powers? Add the powers together. So that gives me negative 16 e to the what? 4x? On the first one. On this one, those cancel out and give me just 4e to the 4x. And on this one, those cancel out, leave it plus e to the 4x. Okay, and the backwards diagonals, let's see what we get there. Y'all probably ahead of me. It's going to be 16 e to the 4x. Cancel out plus 4e to the x. 4x me. And then this will be negative e to the 4x. And that doesn't equal 0, does it? Let's count this up. This would be negative 16 plus 4 is negative 12, negative 11, minus 27, minus 31, plus 1. Negative 30 e to the 4x. So it's not equal to 0. What's our conclusion there? Linearly independent. All right. This stuff is not on the test next week. Cuts off on the word problems. Okay?